Dear friends, last time we have defined closed set in a metric space, and we have seen some examples of closed sets, and this is actually the definition that we have in the last lecture. Now today we will prove some theorems on closed set, and before that we will just quickly revise what we have studied. The definition is E is closed if closure of E is equal to E, and closure means the set of all limit points of E, that is closure, and it is closure of a set is same as the set E, then the set E is closed. And we have seen earlier that E is always contained in closure of E. So to prove the equality, we have to prove the remaining part, that means closure of E is contained in E. Then these two will be equal. That is the definition of E is closed. And one more important result that we have studied is X belongs to closure of E, means X is a limit point of E. If and only an open ball about X of radius R contains a point of E, at least one point of E. That is a theorem that we are going to use to prove the next result, that is theorem number 8. And this number 8 is written in consecutively, including the earlier theorems of open sets, etc. So the theorem states that if E is any subset of a metric space M, then closure of E is itself closed. Closure of E is closed, or that is closure of E is equal to closure of E, or double closure of E. That is according to the definition, because when E is closed, closure of E is equal to E, and when E bar will be closed, E bar is equal to closure of E bar. So that is the result that we have to prove. Now we shall consider the proof. See, we have to prove that this part only. That means double closure of E is contained in E bar. So we need to prove this. We have to prove that the part that is contained in E bar, since E bar is contained in closure of E bar. This is by corollary. So we need only to prove this, and for that purpose we will consider X belongs to double closure of E, and then we shall prove X belongs to E bar. So we have to prove that let X belongs to closure of E. Then we shall prove that by subset relation. When we prove this subset relation, this set is subset of this one, every element in this set is again an element in this set, then this first will be subset of second. So let X belongs to this left side set, then we shall prove that X belongs to closure of E. And that is when and this is the theorem 7, here we have to consider. When we say X belongs to closure of E, that means if and only an open ball B of radius R about X contains a point of E. So we have to prove that X belongs to closure of E, that is open ball B of radius R about X contains a point of E. So this is what we have to prove. Now we shall start with this again. Now X belongs to closure of E. So then we will consider let. Now let. Then and what is meaning of this, again by the same theorem. There is an open ball B of XR which contains a point of E bar. Now E bar, not E double bar, because if X belongs to E bar, we say BXR contains a point of E. So one bar will be removed. So then BXR, open ball about X, contains a point. See, we shall say, suppose a point B denoted by Y contains a point Y belongs to E bar. This is by Theorem 7 for reference. So earlier theorems are important. We have to use the earlier theorems. Definitions are all important to prove the next results. And thus X belongs to this double closure means the open ball B of XR contains a point Y belongs to E bar. And what this shows that if this is a point in this open ball, the open ball is of center X and radius R. This is BXR. And this open ball contains a point, what we have written is, this open ball contains a point Y. And therefore what is the distance between X and Y is certainly less than R. Then only the point will be in the open ball. So this implies the distance between X and Y is less than R. And now we shall assume that distance to be S. Suppose this distance is S and distance we denote by rho. Let rho of xy is equal to S, and we take t greater than 0 such that t is less than S minus R, R minus S we should consider. T is less than R minus S. R is greater and S is smaller. So let the difference of R and S be T. So we will consider T is less than that difference, R minus S. Now again we consider this point. Y is in E bar. Further, Y belongs to E bar. Means again by theorem number 7. So an open ball about Y contains a point of E. So this implies B Y, and now this open ball we will denote by radius of radius T. R is used here. So an open ball about Y is B Y comma T contains a point of E, and that point we will write as Z. Z belongs to E by theorem 7. This is for your reference, the theorem is quoted. And thus this open ball of radius T and about Y contains a point Z means the distance between Y and Z is less than T. So this implies rho of Y and Z is less than T. Now what we shall consider is the distance between X and Z. Actually what we have considered is open ball around Y of radius T. This is radius is T. And this contains a point Z. This contains a point Z, and Z is in E. Now we are considering distance between X and Z. Now that distance between X and Z we will consider the triangle inequality. So this distance is less than or equal to rho of X and Y, X to Y and then Y to Z, that we will consider, plus rho of Y Z. So this is by triangle inequality. And now you see so this is rho x z, left side is rho of X and Z, and that is less than or equal to. What is the rho of X and Y? We have assumed it is less than R. So or by this condition we have it less than R. So therefore the relation will be strictly less than R. And this is R. And what is the rho of Y and Z? That is less than T. So therefore this will be less than r plus t. And again, what is t? T is again less than r minus s. So therefore this is less than r minus s. That is less than r plus r minus s. Since t we have selected which is less than r minus s. But what is this value is, see here, it is actually we should have, this is less than r, and we have this row of x and y, this is less than r, that is right. And what we have selected is t should be less than see s minus r, we will but s is smaller than r, and t we have selected less than r minus s, so it is r minus s. And this is, so row of xy, we should use this row of xy is s, and therefore this must be s. Row of x and y is s, we have supposed, and therefore this value is to be replaced by s. This is the correction, you note. Row of xy is s, and row of yz, row of y and z is less than t. So we should use this one. And then this is less than, s is as it is, and t is less than r minus s. Now here s cancels and r remains, or this is equal to r. Thus finally what we have is row of x and z. Row of x and z is strictly less than r. And what that shows, the distance between x and z is less than r. Here in the picture we can see. And therefore z is in the open ball bx comma r. So this implies, z belongs to the open ball of radius r about x. And what about z? Z is a point in E, and z belongs to E. And what this shows, the open ball b of x comma r contains a point of E, and this is what we wanted to show. Hence the open ball b of radius r about x contains a point of E, and this completes the proof. This contains a point of E means x is a limit point of E. That is, this implies x belongs to E1, and thus hence the x belongs to E. We have started with x belongs to double E bar, E double bar, and then we have proved x belongs to E bar. Then this is subset of this one. Hence, thus this completes the proof. So thus we have proved the first theorem in this closed set. Now we will consider the next one, that is theorem number 9. In any metric space M, M row, the set M and the empty set phi are closed. Both empty set phi, the set M and the empty set phi are closed. Both are closed. M and entire set M and empty set phi are closed. So the proof. Earlier in open sets also we have proved M, the entire metric space M and the empty set phi are both open. Here they are both closed. That means the entire set M is open as well as closed, and the same thing about the empty set phi, it is also open as well as closed. So the entire set M contains all points. The metric space M contains all its limit points. And therefore M is closed. So because we are considering the points inside M only, whatever consideration for the sequence, sequence is considered as a point in M, or if you consider subset of M and then we are E, and then we are considering sequence of points of E, and that converges to point X in M. So therefore M contains all its limit points. No point outside M is considered, and thus the metric space M contains all its limit points. Therefore M is closed, or hence M is closed. And what about phi? This is a trivial, but is to be noted the result. The entire set M is closed and the empty set phi is closed. So here you may consider both the sets M and the empty set phi are closed. So next, the empty set phi contains no point. Contains no point in it, and therefore it contains all its limit points. So how this is so? There is a no point in the empty set, and therefore we can say empty set contains all its limit points, because actually there is no point in empty set which dissatisfies the condition of closed set as well as open set. So there is no point which violates the condition of a closed set or an open set, and therefore phi is said to be both open and closed. That is the simple reason for why phi is open as well as closed. So empty set contains no point in it, and hence it contains all its limit points. So because there is no sequence form, and therefore the limit, there is no limit form, and therefore we can't say that it does not contain a limit point. So it does not contain point, but it contains all its limit points. Hence it contains all its limit points. Therefore phi is closed. So this is the meaning why M is closed and phi is also closed. Now we shall consider the next result about, earlier we have proved about open sets. So arbitrary union of open sets, we have denoted open set by G. Arbitrary union of open sets is open, that we have proved. Or see, arbitrary union, any number of union, finite or infinite, countable or uncountable, union of open set is open. And we have proved that finite intersection of open set is open, that we have proved as G1 and G2 are open sets, then their intersection is open. Now the result is that is a complementary result. Here instead of arbitrary union, we will say the arbitrary intersection. Arbitrary intersection of open set of closed set is closed, and the arbitrary here we have denoted there also G. G is open set. Family of F is family of open sets. Here we shall consider F is family of closed set, and this is closed, this is open. If G is open, then union of G is open and intersection of G is open. G1, G2 are open. So these are the results about open sets. And what about the instead of complementary results, instead of union, arbitrary union, here arbitrary intersection of closed set is closed. F is closed. Here. And what about the second result is intersection of, instead of intersection there will be union. F1 union F2 is closed. So these are the two results we have to prove about closed set, and these we have proved about open sets. Now first we shall take this result. F1 union F2 is closed when F1 and F2 are closed, and that is our theorem number 10. If F1 and F2 are closed subset of a metric space M, then F1 union F2 is also closed. That is the statement of the theorem, theorem 10. If F1 and F2 are closed subsets of a metric space M, then F1 union F2 is also closed. Now we shall prove it. How to prove F1 union F2 is closed? As earlier, we shall have to prove the closure of this is equal to the same set. E is closed if closure of E is equal to E. And to prove this, we need only closure of E is subset of E. And instead of E, here it is union. This is to be closed, means we have to prove. We have to prove that closure of F1 union F2 is subset of F1 union F2. So this is what we have to prove. And since we have always this is closed, this is subset of, right side is subset of left side. Since F1 union F2 is subset of closure of F1 union F2. This we have a corollary. E bar, E is always closed in E bar. So we need only to prove this. So to prove a closed set, we need closure of that set is contained in the set. And now to prove this subset relation, let X be in this set and prove that X is in the second set. So for that purpose, let X belongs to closure of F1 union F2. And X belongs to this closure means X is a limit point of this F1 union F2. And X is a limit point means there exists a sequence Xn of points in this set which converges to X. That is the meaning of this statement. So this implies there is a sequence Xn of points in F1 union F2 which converges to X. This is the meaning of limit point, or the point is in the closure which converges to X. And what this implies, there exists a sequence in this union of two sets, means this sequence must have a subsequence of points in F1 and also points in F2, or points in F1 or points in F2. Union, meaning of union. If an element belongs to A union B, means that belongs to A or that belongs to B. So therefore this implies there is a subsequence, or Xn has a subsequence. We may write the relation in implication. This implies Xn has a subsequence whose points entirely lies in F1, or has a subsequence, or it has whose points wholly lie in F1, or meaning of this union, or it has a subsequence points in F2. It has a subsequence of points in F1, or Xn has a subsequence of points in F2. And every subsequence converges to the same point as the sequence converges. We have a result from sequences. If Xn is a sequence and that converges to X, then all its subsequences converges to X itself. So, but a subsequence of Xn must also converge to X, and therefore that point X must be a point of closure of F1, or X is a limit point of this subsequence, and that limit point must be limit point of F1, and that limit point of F1 means X belongs to F1 bar. So this implies X belongs to F1 bar. X is a limit point of F1, or that is equal to F1. Why F1 bar is equal to F1? Because F1 is, and both F1 and F2 are closed, and if they are closed, closure of that is equal to the same set. This implies X belongs to F1 bar is equal to F1, or X belongs to F2 bar, which is equal to F2. The reason for this is since F1 and F2 are closed. And what this implies, see, X belongs to F1 or X belongs to F2. So this implication we have written here, and thus X belongs to their union, F1 union F2. And thus starting with this X belongs to closure of F1 union F2, we have proved that X belongs to F1 union F2. And that means from these two parts we can say that this first set is subset of the last one. And thus closure of F1 union F2 is subset of F1 union F2. And this is what we wanted to prove. And this completes the proof. So thus we have proved that union of two closed set is also a closed set. But we have proved the result for union of two, and this can be extended to union of finite. But whether infinite union of closed set will be closed, that we should check, and we write it as a remark that infinite union of closed set may not be closed. An infinite number union of closed sets of a metric space need not be closed. This is we shall verify. An infinite number of union of closed sets of a metric space need not be closed. This happens for only finite. That means if n number are there, finite number, 3 may be there. If F1, F2, this can be extended to n number, finite number. Then their union is also closed. But this is not true for infinite number of union. For example, we can consider this example. For example, first union of n taking value 1 to infinity of this set, say 1 by n and 1 minus 1 by n. What will be this union? Now you see it is infinite, and each set is closed, because we have earlier seen that closed intervals are closed sets, and therefore these are closed sets. But the first, if you take the value of n as 1, So 1 and this will be 1, and but this will be 0. So 1 0 is not an interval form. And then the other intervals will be 1 by 2 and 1 minus 1 by 2, that is 1 by 2 single point, and so on. So as n goes up to infinity, see this will approach 0, because we know that as n tends to infinity, 1 by n tends to 0, and therefore this will approach to 0 and this will approach to 1. 1 minus 0 means 1, or actually this is, and it is approaching and not equal to exactly. So therefore this is very very close to 0, means open interval we have to consider, not equal and not exactly equal to 0. So therefore this will approach to 0 and this will approach to 1, not exactly equal to 1, and therefore the interval of this union becomes open, 0 to 1. You may verify this. So we discard the first set, and the second is half. So this is half, means singleton half union, and then the 1/3, 1 minus 1/3, that is 2 by 3, and so on. So and the union of all these will be between 0 and 1. So but 0 is not a member of this, it is limit. When n becomes very very large, it is close to 0. So therefore it is not a member of this, and the set is open. So second example can be considered as union of n taking value 1 to infinity, say 1 by n, and this another point can be considered as 1, or we will consider this as closed 1. So this must be closed interval. So 1 by n and 1. So here what happens, this 1 by n as n tends to infinity will approach to 0, and this 1 will remain the same. So this will be now 0, and this end is closed because 1 is fixed. Here both are limiting value, and therefore the interval becomes open. But here this limit of 1 as n, it is independent, so it is fixed. But this interval is not open. This interval is not open, and this is closed. This interval is not closed. This interval is not closed. We have written half open intervals are not closed. So this is not closed. This is closed. This is union of infinite union of closed sets, but it is not closed. Here also it is infinite union of closed sets, but it is not closed. So these are examples for this remark. And one more result we shall prove, and that is theorem number 11. We will have. So I shall write that theorem statement here. Let F be a family of closed subsets F of a matrix space. It is a family, means maybe infinite number of closed subset it contains of a closed subset F of a matrix space M. Then intersection of F, where F belongs to, this is a script F, we have used this notation earlier, script F is closed. So the proof for this is to be proved as closed, means we have to prove that its closure is equal to the same set. We have to prove closure of this is equal to the same set, or to prove this, that is to prove this is subset of this one, because the other side is always true. This set is subset of, a set is subset of its closure. That is to prove closure of F belongs to the family F family of closed subsets means it has a collection of closed subsets, and we are taking the intersection of this. So this example also we have considered in union of open sets. That means F contains, the meaning of this is, if F contains F1, F2, F3, etc., then we have to take the intersection of that infinite number of. So this is F, and it contains F1, F2, F3, etc., infinite number, and then intersection of this F belongs to F means F1 intersection, F2 intersection, and so on. So why we are not writing 1 to infinity, that becomes countable. Here it is arbitrary, means may not be countable. So this is the meaning of intersection of all sets in the family is closed, and we have to prove this is subset of intersection of F belongs to script F. Now for that purpose, let X be the element in the left side set, that is intersection of F belongs to script F. So what this implies, X is a limit point of this, and therefore an open ball about X contains a point of this. So by theorem 7, so this implies open ball B of radius R about X contains a point of this intersection, contains a point, well, let us denote that point as Y, contains a point Y belongs to the intersection of F. F belongs to script F. And see what this means. Y belongs to intersection, and by the definition of intersection of set, Y must be in every member. Then we say Y is in the intersection. So therefore, for every F belongs to F, this family, Y is in this open ball of radius R about X. So therefore, for every F belonging to F, the open ball of radius R about X contains a point Y, contains Y belongs to F. Y belongs to F for every F, and thus Y is a limit point of every F. So what this shows, for every F in this set, this open ball contains Y belongs to F. So this implies Y is a limit point. Y is a limit point of every F belongs to F. Or that means this implies Y belongs to F bar, and F bar is equal to F because F is closed. Closed subset F. F is closed means Y belongs to F bar, which is equal to F for every F belongs to F. And thus this implies Y is in every F means Y is the intersection of F. This implies Y belongs to intersection of F. F belongs to F. And thus we have proved, considering this, say Y is a limit point in this. So we must have the point X. X must be limit point, not Y. We have started with X. X is in the intersection of this set, and this contains a point Y. So therefore every of this open ball BXR contains a point F, and therefore X is a limit point, not Y. We should note X is a limit point of every. It is open ball around X. So therefore X is limit point of every F, and this is a correction. So X is a limit point of every F belongs to F. So therefore X belongs to F bar for every F, and this implies x belongs to intersection of F. And the starting with x is in the closure of this intersection, we have proved x is in this intersection means this is the first is subset of this one. So this is what we have to prove. Hence this result. Hence closure of this is a subset of the intersection of F, and this completes the proof. So thus we have proved few results or theorems on closed sets. So please go through these results and try to understand these results. Remaining part we will continue next time. Thank you.